Last week with magnetic particle inspection, we got into kind of the theory behind it, right? We looked at some of the important key points real quick. The parts of the hysteresis curve and things like saturation, right? Getting all the atoms in a material magnetized or aligned to create the strongest magnetic field. When we shut that off, materials are going to exhibit retentivity. They're going to stay magnetic for a period of time. And then you actually have to reverse that force, that magnetizing force, to get it to become non-magnetic again, or that's known as coercivity, okay, coercive forces, which is point C on the graph there. And then as you increase that force the opposite direction, you're going to get a magnetic field that flips, and it'll eventually saturate in the opposite direction. And so that kind of goes back and forth on our AC bench we'll be using. It's 60 times a second. And so at any point, we're putting fluid on. Hopefully it catches particles when it hits a saturation point. But at the end of the day, your part's going to typically end up at that retentive point. And just some things there. Permeability, the ability for a magnetic field to form in an item, or in a material. So soft iron is highly permeable, but it's not very. It has low reluctance though, which means those are opposites of each other. So you can get that magnetic field to form. It doesn't resist forming, is what reluctance is. So whereas hard steel is kind of the opposite. It's got lower permeability. The magnetic fields don't form easily, which causes high reluctance. The trade-offs there, though, is when you remove the magnetizing force, a soft iron has low retentivity and results in low residual magnetism. So it really only magnetizes while you're running current, versus a permanent magnet, like a horseshoe magnet or a bar magnet, is made of hard steel. And once it is magnetized, then it will stay. It doesn't want to demagnetize. So it's basically materials where it's easy to get the poles to align. It's also easy for them to scramble back up again. Whereas things where it's hard to get the poles to align and get that magnetic field, it takes a lot more work to undo that as well. And so sometimes you may need a couple demagnetizing passes to make that work. And then the other part, remember, is the flux travels through a part when it hits a crack or any kind of discontinuity. So it can be a crack, it can be a change in geometry, it can just be a rough surface. That flux, that magnetic field, is going to jump those gaps, and it's going to cause things to stick. It's going to cause ferromagnetic particles to stick. And if we put a fluorescent coating or a dye on those particles, then we'll be able to see where there are cracks. But it's also going to end up in things like corners, again, rough surfaces, and things like that. So we went through the MPI process. Just a quick summary. We need to clean the part, magnetize it, apply the particles, check that it has a field, inspect. When we're done inspecting, we want to demagnetize. And again, verify that the field's gone by checking it. We clean off the inspection materials, clean off the carrier solution and particles, and then we've got our results. So getting to where we are, the bench we're going to use looks something like this. This is a little bit more modern version, but the different parts there. So you have a control panel on the front face that allows you to set amperages and turn the current on and off. You've got the headstock and tailstock, which are these parts that they do two things. So here's the headstock on the left, and the tailstock is on the right. And those clamp the part in place. They're going to be what holds the part, but they're going to have a copper pad on the front of them that allows us to hook basically to create a conductive bond with that part, so we can run a current through it in order to get that magnetic field. We then have a coil that can go around the part, so that head and tail stock, they're going to run current through the part. So if we run current through the part, which way does a magnetic field form? Where's it going to form? Remember, does a magnetic field form parallel or perpendicular to our current? It's going to be perpendicular. So it's going to create like little rings almost around the part. Whereas if we use the coil here, we can run electricity through this coil in the middle. And that runs current around the outside, or makes a ring of current around the outside of the part. So it's gonna create a magnetic field going left to right in this case, through the center of the part, kind of turning the part into a giant bar magnet. And then underneath this, there's a tank that has fluid in it with your particles, carrier fluid, with some manner. In this case, they've got an applicator, a little nozzle. And then on the right side here, they show a inspection light, an ultraviolet light, or this can be a separate flashlight. We've got flashlights that you can use as well for that kind of an inspection that are a little more portable. So when we're running it, the two ways we can run current are called longitudinal field or circular field. So the longitudinal field we use, it runs the length or along the part. Okay, along the length of the part is the longitudinal field, and that's what we use the coil for. So that coil is going to do that. And typically you get a field that's going to be strongest or strong enough to perform inspection 6 to 9 inches on either side of that coil. So on a particularly large part, a longer part, you may have to set the coil, that coil's on rollers, you can move it left to right. You may have to put it closer to one end and do your magnetization and particle application, and then slide it or roll it over to the other end a little ways, and then do that again in order to magnetize the entire length of the part. Okay. So there they show a crankshaft would be an example of a part you might have to move it side to side. So that's a longitudinal field using the coil. Excuse me. So if we look at what that looks like, just kind of a drawing of it. So you can see the magnetizing current here, that coil that surrounds the part makes these circular current lines, the dashed red lines. And then the magnetic lines of force, or the flux, you can see are the large red lines going left to right there. And they show them going left, but again, we're using AC, so they, your north and south poles may be left and right, or they might be right to left. We don't really know. There are ways you can figure it out with a Gauss meter, but it really doesn't matter. We just want the part to be fully magnetized. We don't really care which direction, left to right, right to left, our magnetic field is running. Okay. Where that is important, though, is you can see we've got several different cracks there. So we've got a longitudinal crack going along the length of the part. And in that case, because the magnetic lines of force are not going across it or jumping it, so to speak, they're running parallel, you really won't get much indication there. The transverse defect, however, on the opposite end, on the right side, will cause those magnetic, those flux lines are going to have to jump from one side of that crack to the other. So that will show up. So we need to magnetize most parts in two directions in order to make sure we see it. And in fact, when you come into lab, when I'm showing you how to use this equipment, the part I have it works really well for showing the difference. When I magnetize it one way, there are some cracks you can barely see. When we turn it 90 degrees, they show up really, really well. So that's why I use it for example. The 45 there, is something in between, but you can see it's still going to cause flux to kind of jump or go from one side to the other. So typically 45 degree or some kind of an angle, anywhere between 45 degrees and 90 degrees to the magnetic flux line should show up fairly well. If it's between zero, if it's parallel to 45 degrees, it's not going to show up as well. Now we can take that part, we put it in the head and the tailstock, and typically this picture, that's the one thing I don't like about this picture is you don't normally have this part clamped in the head and tailstock anyways. You're going to use the head and tailstock to support the part in the ring as well. But here, now, if we have our head and tailstock, we can run current. You can see the copper pad pretty well in this picture on the left side there. So there's this copper pad. My pen's not the greatest, but Let's try this. Right over in this area. No, that's not much better. So there's a copper pad there that the end of the part is butted up against, and there's another one on the tailstock side as well, which is on the right. And that's going to allow current to flow into or through the part. And so when we're doing it this way, now you can see our current here, they show going left to right through the part itself. And that's going to create these little rings of magnetic fields. Okay. And again, so now the opposite of true, that longitudinal crack, a crack running against the magnetic field parallel to the current. That's going to show up really well. The transverse crack on the right there probably won't show up much at all. And then you've got the 45, there's different angles of cracks in between. It'll vary. And then irregular cracks, that can really depend on where they are, what the angles are, that kind of thing. So by running current in two different directions through the part longitudinally with a circular field, and running a circular current through the coil, so we get a longitudinal field in the part, we're able to make sure we don't miss any of those cracks that may be running in different directions. Okay. The last method we do is for a circular part. And when we have a circular part, we can't really clamp it very well. There's not, first of all, some of these, especially if you're using small gears and that kind of, you might not be able to clamp the head and tailstock together close enough to do it. But the other part is just the way the magnetism builds up in it. If you're using something that's ring shaped, and this could be a gear or like that, what they show there in this picture is a sleeve out of a landing gear, like the steel bushing sleeve out of a landing gear strut. And in this case, what we have to do is support it somehow. We're not going to clamp it directly. And so we take a non-ferrous rod, typically it's brass or copper or bronze. Brass, copper, bronze are going to be your three non-ferrous. Very conductive, but non-magnetic. And that's actually, you're going to run that through the middle of our circular part. And then that gets clamped into the head and tailstock. Okay, so current now can flow through that rod. And so again, this is things for gears, tubes, rings, parts of landing gear, the circular tubes and that kind of thing. But when we do that, what it's going to do, there will be, even though the rod is non-ferrous, it's not going to hold a magnetic field. When we run a current through it, it will create a magnetic field while the current's running. Okay. As soon as the current shut off, however, that rod will not remain magnetic at all. But the part, if that magnetic field has intersected a part that's hanging on the rod, that will become magnetic, and that, depending on its retentivity, that should retain a certain amount of that magnetic field that was developed. And so what happens is it magnetizes around the circumference of the part, and it goes a distance, it's 4 times the diameter of the part. And so what I mean by that is if we have a part, and I'll try to draw it on here. Let me go back to this blank screen. So if we have a part, and here is our roughly circular part. A very nice circular part. You can all see that. Okay. And we take a copper or brass rod and we run it down the middle right here. Okay, there's our rod running through the middle of it. The magnetic field is going to form roughly 2 diameters of that rod each side of it. So, our diameter is the distance across the rod here, left to right. So if we kind of go 1, 2 diameters here, and 1, 2 diameters here, when we run current through this rod, we're going to magnetize about that much of our circular part. Okay, that top portion there between the blue arc. So, okay. And so what'll happen is we can't magnetize the entire part at once. So one thing you want to do, you want to use the largest rod that you have available that will fit in the part, right? Because that's going to magnetize more and more of the part. The other part of it is we're going to have to rotate our part. So we test one section of it, and then we'll rotate it, and we'll test another section, we'll rotate it, and we'll test another section. And we'll look at how to figure out the rotations here in a couple minutes. So when we put it in, it's going to look something like this. So here's an example of a gear that's on a central conductor. Now this is kind of a skinny central conductor for the gear, but it will work. Again, if you had one that was a larger diameter central conductor, a larger diameter brass rod, that would be even better. One thing you do have to be careful, like you see this one, it's a fairly long rod. If you run a fair amount of current through this, what's going to happen? It could, before it melts, what'll happen? Okay, and when a metal gets hot, particularly a brass or a bronze, it can get soft and it can start to sag. Okay, so you need to run the current, but you got to be careful not to overdo it. And the skinnier the rod, the more likely it is that you'll overheat it. Okay. So what happens is you get something going on looking like this. They show a copper bar in this case. And so the magnetic field, it kind of forms around the surface of the part. But it's more, you can think about it as like a circular, almost like a straw around the length of the rod, right? And the places where that straw intersects, if you have a rod and you put a tube around it, the places where that tube is, that's 4 times the diameter. You put a tube around it, the places where that intersects is going to be where you're going to magnetize your part. And so here's a sketch of what I showed you. So you take that diameter and you can see the inner surface here will actually magnetize a little bit further than the outer surface. So if we have this set up, how do we figure out how many times we have to rotate the part? What do we have to do? How many times do I have to turn this part to magnetize the entire thing? To make sure I've inspected and magnetized the entire part. What's that? 4. We have to turn it 4 times? But how do we know? So if we take the circumference of the outer part, and you want to take the outer circumference, okay? Let me switch my pen color back to one that's a little more visible. So we need to take the outer circumference of this, the length of the outside, right? So we take the circumference of the part, we divide it by 4 times the diameter of the rod. Okay? And that'll tell us how many places we have to do it. And then, okay, so just now, how do you get the circumference of a part? I thought there was a way I could type, but I guess not. Anyone remember circumference? You can measure around it. Okay, so one way is to measure around it. What's that? That's the area of a circle. 2 pi r, or pi times the diameter. Okay? So you don't have to know it exactly. If you know, okay, a part is about 2 inches across, right? And what's pi? 3.14, right? Roughly. Well, let's just call it 3.2. So if the part's 2 inches across, we multiply that by 3.2, that gives us 6.4, right? Now, what if our rod is a 1/2 inch in diameter? How many times do we have to turn it? So what's a 1/2 times 4? 2. So we would go 6.4 divided by 2, right? What's 6.4 divided by 2, roughly? What's that? 3.2, right? Okay. So 3.2. So how many times would we have to turn it? What do you think? 3 or 4? You have to do it 4. You always have to round up. okay? Because you want to have some overlap so you don't forget it, so you don't miss it. So, that calculation you can do. So you'd have to turn it 4 times. So you'd have to turn it roughly 90 degrees, right? You'd start at 1, you'd turn it 90 degrees, do it again. You'd turn it 90 degrees, do it again. You turn it 90 degrees, do it a 4th time. Okay. And that way you can make sure you've got your magnetism, that you've basically inspected the entire outside circumference of the part. Okay. And the way you would do it is you would have your ring or your gear hanging on the rod. You would run current through it. You'd run current, put your fluid on, stop putting your fluid on, stop the current. You would do an inspection of it. Then you would turn it, run current through it again, put fluid on, stop, inspect it again, turn it again, and do that as many times as you need to do the full outside. So you can see why having a thicker rod might be a little bit better. If you can fit a larger diameter non-magnetic rod, you would have to turn it less times. But you could still do a really big part with a really skinny center conductor. You just might have to turn it 8, 10, or 12 times, right? So you just got to kind of keep that in mind as you're doing that, okay? And you only use, for the central conductor, again, we are only using the head and tail stock. You don't typically use the coil when you're doing central conductor. You can try it. You can see if anything shows up that way. There's no reason you can't. But you get that, in that case, you would just be using the central conductor. It wouldn't be a conductor, it would just be a support. It would just be holding your part in the middle of the coil. But the primary way you do it is using the direct contact method, sending current through the center conductor rod itself, and then inspecting in that manner. Clear this stuff out. Some other stuff, we also are able to do portable magnetic particle inspection, okay? And for this, we use what are called prods. Basically, think of a cattle prod, right? You've probably all seen them, or a taser. A couple metal probes that you send a current across. Well, you basically have two handheld probes. The simplest versions of these are 2 probes that are literally wired to a socket, to a plug, with no control whatsoever. You basically have a switch. They're wired, and it goes right to it. Now that doesn't put out a lot of current, and it's not a great thing. So the ones you typically would use are going to be a little bit more complex. They're going to have more stuff going on. So prods or a yoke is another form. A yoke is a big electromagnet, and so there are portable electromagnets you can use. Another method is with portable MPI is you can basically take a coil of wire. So rather than having a coil that's fixed to your bench, they make versions of these where it's basically welding cable, big welding cables that you wrap around something and then hook it up to a control box of some kind. And then from there, rather than using a liquid bath, which is going to get everywhere, or the liquid carrier that has a bunch of stuff in it, they make dry powder versions. How many of you have played with a magnet and metal shavings? Ever done that? You see the lines? That's basically what they're doing here. Okay, or you can get those metal shavings, that metal powder with different colors on it. It can be bright yellow, green, red, blue. So you can put it on contrasting. If you have a background that's one color, you can get contrasting powders. Or some of these come in like an aerosol form as well. So you shake it up, and it's a suspension. There's basically fine metal powder that's in an aerosol can. And you can use that as well. And again, they can be visual or fluorescent, depending on what kind of dye is in there. So here's an example of a prod system. So they basically have this big power pack there. You can see how heavy duty those cables are going from the power pack to the prods themselves. And these are going to run a current through whatever it is you're testing. So through in like a metal plate, like they show here. And they're holding those prods on that metal plate. It's going to run a current through them. That'll create a magnetic field in that area. And then you can sprinkle a ferrous powder on there and kind of see. And so many of you said, if you take a magnet and you do the iron filings, they end up, nice little arcs going from the North Pole to the South Pole. What do you think happens if there's a crack? What's it going to do? It causes some kind of an interruption to those nice little arcs. You'll see like a weird pattern or something along those lines. Here's an example of a portable yoke. So the prods are running a current through something. These are actually sending power, sending electricity through this metal plate right here. A yoke is a big electromagnet. Okay, so this isn't going to put out any current. You know, you can't walk up and shock your buddy with it or anything. Okay, but you can wipe their phone out if you want, or their watch or whatever. The two ends here, you can kind of bend those green portions. Those are basically just, it's just a big electromagnet in there. You push the trigger at the top and it creates a magnetic field between the two ends of the yoke. Okay, and again, now you can put metal powder in that area, or you can do an aerosol bath in that area, and you would be able to see those lines of flux. And if there's any kind of a disruption to it, it'll cause that, you know, that powder to not lay evenly and that kind of thing. Okay. These do have another use as well. So when we get to the end, we'll talk about demagnetization. We've got to demagnetize our parts. When we had airplanes that got hit by lightning and had part of the lightning inspection is making sure nothing got turned magnetic on the airplane. We'd have to go around with a Gauss gauge, same one we use in the lab, and we'd have to go and check parts, particularly steel parts. So things like landing gear legs, the window frames around the windshield, especially because the whiskey compass is behind it. Fasteners, all your little screws, right? Most of those are steel, even if they're in aluminum. And so if we found something magnetic, we would have to take one of these yokes. So if it was like a landing gear leg, we'd take one of these yokes, we'd bend the two little ends so they kind of wrap around or kind of hug the gear. And one way to get rid of magnetism is to create a magnetic field and then reduce that magnetic field. Turn it down. Or in the case of this, you have a landing gear leg, you put it around the leg, you press the button to activate the field, and you draw the yoke away. And the magnetic field at that gear leg gets lower and lower and lower, and it actually re-scrambles everything. So you do that a couple times. And then you check your landing gear leg to make sure it's not magnetic anymore. And that's how you're going to demagnetize parts on our bench, is you're going to turn the coil on. You're going to hold the part in the middle of the coil, turn the coil on, and draw the part out from the coil. And you'll be able to demagnetize it. So one way is to take the part and draw it away from the magnetic field. The other way is to take the magnetic field, if you have a yoke, and draw it away from the part. Or like if it was the window frame, you know, we'd have a flat surface. You'd take the yoke, put it right by the flat surface or at the top of the window, and turn on the yoke and draw it away, and then turn on the yoke, draw it away. You might have to do it 2 or 3 times. But you'll see these for demagnetizing as well as performing NDT. But they're the exact same thing. There's kind of a pictorial view of what those prods look like and how it creates indications. So you can see these create, so the yoke creates more of a linear field between the two ends of the yoke, whereas when you do prods, you get more of these circular fields. Okay, we're running a current through the part right now. You get these circular fields, and you can see that weld or a crack is going to cause a jump in the circular field. So those are different ways of magnetizing. When we're applying ferromagnetic particles, the way we're going to do it is using what's called the wet continuous method. And this is the aerospace standard, okay, unless you're doing on wing. But most of the time, most of your NDT, most of your magnetic particle inspection is done off wing. It's parts that can be removed, they're inspected, and then they're going to be reinstalled at a later time. So our particles are carried in a light oil bath. And the light oil bath, it's called a carrier solution. Okay? It's very similar to mineral spirits. It's a very thin, oily kind of liquid. And what it does, it's called a suspension vehicle. So the particles don't dissolve in it. They're always suspended. And so we have to mix them up or agitate them. And then when you stop, if you stop mixing them up or agitating them, they're all going to settle to the bottom. They settle back out of it. So we carry them, we suspend the particles in the oil bath. We're going to turn on current and apply that carrier with the particles to our part. Okay. And then what we're going to do is, while we're continuing to run the current through the part, we're going to stop applying the liquid. And then we shut off current. And that whole process is pretty quick. So you press the button, you start putting liquid on the part, you press the button, you draw the liquid away, and then you release the button. And it takes all of 1 to 2 seconds. Okay? You shouldn't be running the machine more than a couple seconds. So again, putting liquid on, press button, pull away, release button. Bigger parts may take a second or two longer, but at the end of the day, you should never be running it for more than 1 to 2 seconds normally, maybe up to 3 or 4 seconds if you got a really big part. Okay, we don't want to run that current longer than we have to. It magnetizes pretty quick. So bath is applied with current. There are cases where in some applications you can magnetize the part and then go back and apply the ferrous materials later. It's known as residual, but it's not as sensitive, okay? Because part of that applying the particles means you're rinsing off a certain amount of the particles. So it's not often used in aerospace. And then dry particle testing for portable. So dry can be residual or dry can be continuous as well. So dry residual is you hit the part with the probes or the yoke, you magnetize it, you remove that current, and then the particles are almost a dust. They're applied in like a little puffer type thing. It's like a little bulb that you can squeeze and it blows out little puffs of this dry particle stuff. Or continuous is you're running the current while you're puffing the particles on at the same time. So here we are applying the fluid, okay, and they're holding the button right now. There's the little puffer in the dry system using a yoke. Okay, so dry continuous using a yoke instead of, and here's just what some of those look like. So like I said, they can come in different colors in order to provide the best contrast. So like there, it's on a white background. You probably wouldn't want to use those gray or white particles if your material was gray or white, but you can see like that green or that blue give a real nice contrast, right? Or steel, sometimes if it's rusty, if it has a layer of rust on it, you can still perform magnetic particle inspection, but you probably wouldn't want to use a red or a brown ferromagnetic particles because they blend in with it. So, and then some of the others shown here, the top two are MagnaGlow 14A and MagnaGlow 20B. We use MagnaGlow 14A. So this is a little canister of the particles that we mix in with our carrier solution. So these come separate. You can't buy the liquid carrier with the particles already in because you have to be able to adjust the concentration. Over time, the concentration will change. Every day you go to test, you're going to have to test it. We'll talk about that in a minute. But you'll get what's called draw out, and that is as you test items, some of those particles stay stuck to them even when you're done. You go clean the part in a washer somewhere, and now you've just reduced the total number of particles that are in the tank. So over time, the level in a testing bench is going to drop. So you have to be able to add more of the particles to bring it back up to the required concentration. And then there is, like I said, it's available in aerosol as well. And those are all the 14A, the 20B, and the aerosol are all typically going to be, they're going to be fluorescent. Okay. So a quick lesson in fluorescent inspection, because this is for both mag particle. We're talking about a mag particle here, but when we get to liquid penetrant, dye penetrants, it's going to apply there as well. So just a quick review, here is the electromagnetic spectrum, cosmic rays, gamma rays, X-rays on the left, going all the way up to, so those on the left, then we have ultraviolet, which is going to be important for us when we're doing this kind of testing. As the wavelength continues to get bigger, we get into infrared. Well, we have the very narrow visible light spectrum, then we get into infrared, microwave, radar, radio, and broadcast. So the stuff on the right is cell phone and radios and communications and that kind of thing. And then we've got our visible. You can see that very narrow band kind of just left of center. If it's spread out, is our visible light spectrum, right? So for fluorescent particle inspection, what fluorescent means is they are materials that are excited by ultraviolet light. Okay, and they give off, or they fluoresce. They give off light of their own, so to speak. So if we take long wavelengths, so the longest, remember this goes shortest wavelength on the left, longest on the right. Long wavelength ultraviolet light is that ultraviolet light that's nearly to the visible spectrum. So long wavelength ultraviolet light is right in, it's going to be hard to see, right in this area right here, right on the left edge of the visible spectrum. Okay. And that's what's known as, many of you are probably familiar with black light, okay? It makes your stuff glow, but it doesn't give you a sunburn. Okay, whereas regular ultraviolet, you can hit these fluorescent chemicals with true ultraviolet light, and they'll glow, but in the process, you'll also give yourself a sunburn, possibly cause eye cancer. You know, you can get retinal cancer from it. So you don't want to have a lot of exposure to it. So that black light gives us that nice happy medium. So black light is in the 3,500 to 3,800 angstrom range. It has a wavelength of 350 to 380 nanometers. Okay, very small. So ideal for us is 3,650 or 365 nanometers. So you can see where that is. You know, it's just left of the visible spectrum, which runs from just under 400 nanometers up to just over 700 nanometers. So the lower lights, the lower limit of visible light's 380, and we're going to be in the 3650 range. Right there. Oops, I thought I got rid of that. So we're going to be looking in this range right here. Okay. What it means is when we're working with our lights, a light, any one of these UV lights, or one of these, black lights, any kind of a light source never gives out just a single wavelength of light. So the light sources that we have, they have to be able to give out light that is shorter wavelength, more towards the UV spectrum, and longer wavelength. We don't want longer. We don't want visible light. If there's visible light presence, it's going to make it harder to see the fluorescent light, right? So the flashlights and the lights we'll be using for this, they do generate a certain amount of ultraviolet light. Now they put a filter in front of the lens to try to filter it down to just that 3,650 angstroms or 365 nanometer range. But there is a very small amount of ultraviolet light that still does come out of these things. So using it, pointing it at your objects, you know, inspecting stuff, that's all fine and good. If it hits, you know, if you're putting it on your hand a little bit, it's not going to cause a big sun, you know, you're not going to get like a sunburn from it. But you definitely don't want to be turning the thing around and pointing it into your eyes. Okay, your eyes are the most sensitive to being damaged by UV light. And the big thing with them is you cannot feel it. If you're staring into an ultraviolet light, you will not feel it damage your eyes, okay, until after the fact. So again, they're tuned to 365 nanometers, but they do put out some UV light. They do put out some visible light. You'll be able to see when the light is on as well, but we try to filter it down to that. Okay. So that's the part of the spectrum that our lights generate that we're using to excite that fluorescent dye. The other thing we have to be aware of is our current. And so what you'll see is this is taken from an engine overhaul. I can't remember if it's for the 0470 or the 0200. But we need to know how much current to run through a part. We want to get to the point where the part is to that saturation point, right? Where every polarized atom is lined up. But at the same time, we don't want to overdo it. If we send too much current through the part, we could potentially damage it. We could melt it. We could heat it up. We could heat it up to the point that it basically heat treats it and changes the metal's properties, makes it more brittle than what it should be. And so you can see here, this is kind of a guideline. This is based on engine parts of how much current we need to run through a part to reach that saturation point. So at the top there, the crankshaft, you can see is 2,000 amps. We gotta run 2,000 amps through it. Connecting rod's a little smaller, 1,500 amps. When you get down to things like rocker arms, You can see 800 amps. You can see rocker arms actually have a difference. They are 1,000 if you're using the coil, because the coil's not running. Oops, the coil's not running power directly through them, right? But if they're between the head and tail stock, they drop it down to 1,800. Or you get down here, through bolts and rods, they're only at 500 because they're so skinny. So if we run too much current through those, there's a potential we could damage them. So we have these charts. I don't have charts for every possible part you could test in there, but you can kind of get an idea of size, right? If you're going to put a part in that's similar in size to a crankshaft, you're going to need to turn that current way up. If you're doing kind of a little part or something skinny, like a valve or a valve stem, right? You got to back that current off quite a bit so you don't cause damage and overheat it. So, and that comes into play when you do your self-design projects. If you choose magnetic particle for part of your self-design, you can kind of use this as a guideline for how much current to run on a given part. So, before we start on a given day, I mentioned you need to do a particle concentration check. And so we want to know how much ferromagnetic material, how many particles are in a given sample of your oil bath. Okay. So what we do is we take a 100 milliliter sample, we fill out what's called a centrifuge tube with 100 milliliters. It needs to settle for 60 minutes, and the concentration should be between 0.2 and 0.4 milliliters per 100 milliliters of fluid. And you're going to record that for each test conducted. If you're in a lab doing this, you have to do it. You don't necessarily, when we're doing this in lab here, you don't necessarily have to wait an hour before you start doing your tests. In fact, if it comes out as that amount is low or high, you don't have to redo your test. But if you were in a lab where you were certifying parts, if that concentration came in low or high, you would have to redo any test given or any test done at that incorrect concentration. Okay. And so what'll happen is over time, again, that concentration will go down as particles are kind of pulled out, as parts are clean. And we can add a little bit more of the powder to it and mix it up. Before taking the sample, though, you do need to run the bench and run the pump and get everything agitated. You want to do that for about 10 or 15 minutes before you take your sample. So when you guys are doing this, as you start coming into the lab, I'll be turning the bench on beforehand. So that centrifuge tube looks like this. And there's our particle concentration. So in this case, we've got 0.3 milliliters of particles. Okay.